Very brief review of the three different states of matter. So in a gas, the particles are very far apart from each other. They are far enough apart that the intermolecular forces really don't matter at all. Liquids and solids are touchingly close, and so intermolecular forces come into play. In a solid, the particles are stuck by those intermolecular forces enough that they cannot move relative to each other. In a liquid, they're sticky enough that they're holding together, but they can still kind of squeeze past each other and move around. We see there's a big difference in densities. A gas, such as water, at 100 degrees, 5.9 times 10 to the minus fourth grams per milliliter, whereas liquid water and solid ice are close to 1 gram per milliliter. Big difference in density. The biggest difference between liquids and solids is the amount of movement, right? I kind of already mentioned that. Particles and solids are fixed in place. They can vibrate. It's like the solid state of students, people sitting in their chairs, and you're wiggling and you're coughing and various things, but you're not moving relative to each other. When we have lab, you'll get up out of your chairs and we'll be occupying basically the same volume, but people will be milling about, right? We're still together, but we're able to move. So this is a summary, and we've talked about these things before. Liquids and solids have high densities compared to gases. Gases and liquids both have indefinite shapes. They'll take on the shape of their container. A solid will retain its shape no matter what container you put it in, because the particles can't move relative to each other. Volume, a gas has indefinite volume. It will expand to fill the container no matter how large the container is. But liquids and solids will retain their volume. The volume won't change. And relative strength of intermolecular forces, weak, moderate, and strong. Gases are compressible because of all that empty space between the particles. You can squeeze them closer together. Liquids and solids aren't compressible because the particles are already touchingly close. You can't squish them together anymore. Sometimes you can squish them a little bit. Yeah, and that can be very useful. There are devices where if you squeeze them a little bit, some of their properties change, and you can use those as pressure sensors. But it's not a significant amount of compression. And if you're thinking about something like a sponge, well, the sponge has an awful lot of air in it, and so you can't count squishing the air out as compressing a solid.
I was thinking hydraulics.
Hydraulics, okay, so your brakes, you have a liquid in your brake line, right? And you press on the gas pedal, and that puts pressure on one end of this tube of liquid. Liquids aren't compressible. And so it transfers that force through bends and kinks and all over the place back to your brakes and puts pressure on the brakes to stop the car. If you have a big air bubble in your gas line, your brakes feel soft. You put your foot on the brake and nothing happens until you push further, because first you have to compress the gas that's in the brake line. Chemistry in your car.
It's confusing when you say gas. I think gasoline, but you're really referring to oxygen in a gaseous state.
Yeah, when I talk about gas, I'm not talking about gasoline.
Yeah, it's like gasoline in the brake line.
Oh. No,
Oh,
gas in, yeah.
A little confusing.
It is confusing.
Okay, before you
Uh-huh.
continue, are some liquids more compressible than others? I know there's a small amount of compression.
There is a small degree of compressibility for liquids, and that could vary depending on the liquid. But you know, we're looking at broad categories here. Compared to gases, no liquid is compressible. Can they be compressed a small amount? Yeah, they probably can, but not significantly. We can talk about crystalline solids and amorphous solids. In a crystalline solid, we have a regular repeating pattern. At the end of this chapter, we're going to talk a lot about what that pattern is. Amorphous means without shape. So they're just kind of randomly stuck together. So this is like my son Zach's sock drawer, where he has all of his socks folded in pairs, and they're all just stacked up really neatly. And this is Andrew's sock drawer, which is, you know, if we're lucky, there's socks in there at all. They're just thrown in there, right? No order at all. So Andrew's got an amorphous sock drawer. We've talked about changes in state due to temperature, but changes in pressure can also induce state changes between gases and liquids. If you take a liquid and reduce the pressure, you can cause it to vaporize into a gas. If you take a gas and increase the pressure on it, you can cause it to condense into a liquid. Aerosols, yes, and liquid propane. LP gas, liquefied petroleum gas, is mostly propane. You go to the convenience store or wherever you go and you get a cylinder of propane and you hook it up to your grill in your backyard. When you open the valve, what comes out?
Yes.
A gas. But this thing is filled with a liquid. And if you slosh it, you can hear it sloshing around in there. By compressing, by putting a lot of pressure on the propane, they condense it into a liquid. Now it occupies a lot less volume. And so you can transport a lot more propane than you could if you were trying to cart it around in a gas state. When you open the valve, you're reducing the pressure. Reducing the pressure allows the liquid to vaporize and go into the gas state and come out and go into your grill and cook your food.
So, like, when you're heating up water in a kettle and it's a closed environment, does that mean you're reducing the pressure?
We'll get to that. That's the pressure cooker situation, and we'll talk about that later. You know those cans of compressed air for like cleaning electronics and your computer and stuff? What happens to those when you use them for a while? You get really cold, right? Because as you're releasing that pressure and it's going from a liquid to a gas, it's an endothermic process, and so it's absorbing energy from the outside. And it's also the same idea in the compressor in the back of your refrigerator or in the compressor for your air conditioner. We can cool things by pressurizing them and then releasing them later.
Oh, yeah.
Yeah.